Sorry, I'm a bit late with that. So thank you very much, Simeon, for this very flattering introduction. Just a moment. Well, I just keep it in my hand for now. So I'm really honored to be here today at this fabulous event that has been so well organized as everything, of course, that's happening at IPMU. And I'm going to talk about this work here for two reasons, really. One reason is that this is a work that started at IPMU. It started about 2 years ago when my husband, Domenico, was also a postdoc with me here at IPMU. We're visiting Simeon at IPMU, who was thinking together with his student, Masataka Watanabe, who's in the audience, I'm sure, about this problem of studying theories in sectors of large charge. And since then, this field has really taken off. New people have joined the collaboration on our side. That's Luis Alvarez Gomez at CERN and the Simons Center, and my student, Orestes Lucas in Bern. And also, Simeon has kept doing great work with his own ever-increasing number of students. So that's the first reason I chose this topic. The second reason is, even though I'm a string theorist, you do not need to know any string theory to follow what I'm saying here. This is really basic quantum field theory. But before I launch into the scientific part, let me also say a few words about IPMU. As Simeon was saying, I was among the first postdocs to arrive here. And when it's about a bit less than 10 years ago that I received the offer to come here as a postdoc, and back then, some of our senior colleagues, they were a little skeptical, new institute, so they weren't exactly advising us to do that. However, I didn't listen to them, and I was very excited to come. And I had a fabulous time here. From the beginning, it was a great adventure, and from the beginning, I always felt that IPMU had this very, high positive energy. Everyone was really, happy to be there and, making it work and do great research. And I'm really happy to see that over the years, this has remained like this. It wasn't just because this was a new place. It's still like this today, where it's really an established and recognized place. And I've been coming back over the years, so they're not getting rid of me that easily. And I shall be coming back as long as they let me. And so yes, during the first year when we arrived, IPMU looked a little more like this and not the way you've seen it yesterday. And the first picture that I was taken in one of the prefabs that served as our seminar room at the time. But with Japanese efficiency, you already seen this video yesterday with Hitoshi, it took really a short time for the building to spring up right in front of our eyes. So I went every week to take a photograph from the roof of the neighboring building to really document how it grew. And so in no time, it actually looked like you've seen it yesterday, the fabulous building we've been in. And the next picture was taken on the roof, and you see also the researchers had increased dramatically since the first picture. So yes, it's been great for me to be part of this center in the very beginning when it was just starting out. And I think nowadays, any young postdoc who gets the offer to come here would only be congratulated. I don't think there's anyone left who would say, maybe it's better not to do that. So it's been a great success for everybody. Okay, now for the scientific part. I think that it's pretty clear that conformal field theories are quite an important subject in theoretical physics because they play an important role in many ways. They are the fixed points of RG flows. Of course, they describe critical phenomena. That's a picture of superfluid helium. They are related to quantum gravity via the ADS-CFT correspondence. And of course, the world sheet of the string is described. The theory on the world sheet is described by conformal field theory. However, there's a bit of a problem, namely that most such CFTs do not have a natural small parameter that we could use to do a perturbative expansion. Naturally, these couplings would be of order 1, and so we're in trouble because our most best used mechanism to do physics doesn't really work here. These theories are difficult to access, but of course there are some possibilities. We're not completely lost. If it was a 2D theory, we're in luck. In larger dimensions, we can use the methods of conformal bootstrap, which have been really attracting a lot of attention of late. Or you can do something completely else. You put the system on a lattice and you do computer calculations there. And there are also non-perturbative methods that we can make use of. It's generally a good idea to make use of the symmetries that your system has and to look at special subsectors where maybe some of these things simplify a little. That's basically the approach that Simeon and the rest of us were taking here. We are studying theories that have a global symmetry group. They have to have some global symmetry for this to work. And we study subsectors where the charge associated to this global symmetry is large. It turns out that this large charge turns into a controlling parameter. So we can do, after all, in this special sector, a perturbative expansion. Just to make clear what we're doing, this is not part of the conformal bootstrap. This is another set of methods, even though of late bootstrap people have been using also sectors of large charge, and they have, as far as I understand, there was a talk at IPMU last week here about this topic, so they have verified our results also. The basic idea is that I want to consider a model at the infrared fixed point. If we take the O2 model, we're at the Wilson-Fisher fixed point, so we want to write an effective action, the Wilsonian action, which unfortunately in general contains infinitely many terms. We are forced to include all the terms that are compatible with the symmetry of our system. So yeah, something with infinitely many terms is not very useful if I want to do an actual calculation. But okay, let's go on with it. Let's put ourselves into the subsector of large charge, and let's first find the classical ground state. And this large charge actually breaks Lorentz invariance. That's an important point here. So we want to look for a ground state, and the simplest thing to look for is a homogeneous ground state. You don't have to do that, but it's the simplest thing. So you have a ground state that is homogeneous in space, but it is time dependent. Now we want to look at the fluctuations at the quantum theory around this condensate, and these fluctuations are encoded by Goldstone bosons because we have this symmetry breaking taking place in the sector of large charge. And the general formula, basically the recipe for what we're doing is we have a vacuum, we have Goldstones that fluctuates around it, and all the rest are corrections that are suppressed by the large charge. It turns out that now the Wilsonian action only contains a handful of terms that are not suppressed. So suddenly, in this sector, the Wilsonian action has actually become a useful tool for us to do actual calculations in. I give you a brief overview of what I'm going to say today, the introduction you've just heard. Then I'll discuss the simplest model where we can see what's going on. That's the O2 model. We do a semi-classical treatment to identify the ground state. Then we look at the fluctuations. And I give you our results and, more importantly, their confirmation via a completely independent calculation on the lattice. I'll generalize what I've been saying for O2n vector models. And I'll also show you very briefly that we can go even beyond the vector models. Okay, so the simplest case to look at is the O2 model in 2 + 1 dimensions. In the ultraviolet, that's the Lagrangian. We have here a complex field phi. And we know, thanks to Wilson and Fisher, that this model flows to a fixed point in the infrared, where I can still encode the degrees of freedom as 2 real degrees of freedom. Here we have a radial degree and an angular degree of freedom, chi, and this model enjoys a global U1 symmetry, since I can shift here the angular degree of freedom by a constant. Now let's look at the scales we have in this system. Let's put the system into a box which has a scale r. It can be a cube, it can be a sphere, what you like. And the charge of this U1 symmetry gives us a second scale in this system. The charge density, the square root of the charge density, goes like q to the 1/2 over the scale r. Now we want to put ourselves in a special sector of large charge, which means I want 1 over r to be much smaller than the cutoff lambda of our effective theory, which is in turn much smaller than q to the 1/2 over r, which is again much smaller than the original UV scale. And in this sector, I want to write the Wilsonian action, the effective action. In order to do this, I first have to make an assumption which I will justify, namely that the VEV of the radial degree of freedom is large. Under this assumption, I can write down this action, where I have a kinetic term for the radial and the angular degrees of freedom. Then I have this term where r is the scalar curvature of my compactification manifold. I have two numerical constants appearing here, b and lambda, and I have all these higher derivative terms that are naturally part of the Wilsonian action. There are infinitely many of them, but my point is that they will be all suppressed by the large charge in the sector that I am in. This Lagrangian, the truncated part, is approximately scale invariant. That's thanks to the conformal coupling here. Now I just want to do the semi-classical analysis, which means I want to solve the classical equations of motion at fixed charge. It doesn't have to be large at this point, just fixed. So that's the definition of my charge density. And by solving the equation of motion, I find that the charge goes here with a to the 4. A is the radial degree of freedom. This classical solution at the lowest energy and the fixed global charge becomes now the vacuum of my quantum theory. This means I have a non-trivial condensate. The VEV for the radial degree of freedom we call V, and the VEV of chi dot we call mu, and it goes like Q over V is here the volume of my manifold times this V squared. And we see that chi itself has now a non-constant VEV. That's an important point. The VEV is dependent on the time. This fixed ground state is homogeneous in space, but not in time, as you see. And we now want to determine the radial VEV, V, by minimizing the classical potential, which has this form, and it looks like this. This here is the phi to the 6, V to the 6 part you're seeing. And from here we get this centrifugal barrier, which causes V not to sit in the origin, but to be actually large. V goes like Q to the 1/4. So if V is very large and Q is very large, V will be large, which is compatible with this earlier assumption I made in order to write the Lagrangian that A is very big. It is this fact here that we're not in the origin, but here in this minimum of the potential that will allow us to do things with this theory. This makes basically the theory Gaussian for us. Now, we want to do the quantum story. We want to look at the low energy spectrum that we have, which means we need to parameterize the fluctuations on top of the classical vacuum. Here, the hatted variables are the fluctuations. So A is the large VEV plus fluctuations around. Chi is mu t plus chi hat over V. And it turns out that this is actually a massive mode. The mass is order of square root of Q, so it will not be relevant for our low energy spectrum. On the other hand, here we have a spontaneous breaking of the time translation invariance, which means we have a relativistic Goldstone boson showing up, which has a dispersion relation that is like absolute value of P over square root of 2. So it means we're in the superfluid phase of the O2 model. And of course, the question we're all asking ourselves is, fine, but are these fluctuations really controlled, like I promised? To check, we diagonalized the quantum Hamiltonian, which we can do in this case, and it turns out that indeed all the higher orders are suppressed by inverse powers of Q. I mean, so far I could have just gone to fixed Q, but now when we really take this Q to be large, this will be the controlling parameter. So this formula I showed earlier on, that's really the thing that works for us. We have the classical vacuum that we identified. We have the Goldstone boson that parameterizes the low energy spectrum, and everything else is controlled by the large charge. For a concrete result, we look at the energy of this classical ground state, which has the following form. We have a term that goes like charge to the 3/2. We have a term that goes like charge to the 1/2. And everything else is suppressed, at least as Q to the -1/2. We have two numerical parameters, which we cannot calculate with our methods, which corresponds to the fact that we had these two parameters to begin with in our Lagrangian. And these things here, V is the volume of my manifold, and the Ricci curvature, these depend on the manifold that I compactified on. And now I can use the fact that we have a thing called the state operator correspondence in conformal field theory, which means I can here map flat space via conformal transformation to R times a sphere. In our case, that's a two-sphere. So what corresponds to the anomalous dimension on that side will correspond to the energy on this side. So basically, we have to put in here the values for the two-sphere, and we can calculate the anomalous dimension for the lowest operator of charge Q. And it has the following form, where here, additionally to what we had from the classical case, we have this number here, which is the Casimir energy. You get that from calculating the one-loop vacuum energy of our Goldstone boson. Now, this was a nice result, and people were, well, not everybody really believed in what we were doing, but we got confirmation from the lattice earlier this year. Domenico got in touch with some lattice people who happened to be in possession of a good algorithm that was very suited to our problem because they naturally slice up the Hilbert space into sectors of fixed charge. And they got to work, and they did the calculations, and that's the result. Here, these little squares is the lattice data, and this curve is the two-parameter fit, where these two parameters here were fit to the result. And you see that the agreement is incredibly good. It is really, really good. You cannot, I mean, it's just perfect. And they managed to go up to charge 12, which is for lattice standards is a pretty high charge. However, when you look at it, maybe you notice something about the curve, namely that it actually keeps being very well in agreement with what we said for small charge, which is not something that is not a claim that we made. We are explicitly in the sector of large charge, but this keeps working for small charge, and the obvious question is why, and we don't have a good answer at this point. But it is a bit reminiscent of what happens to the Regge trajectories. Now, I've done the O2 model because that's the simplest, but the truth is that we can generalize this treatment very easily to general vector models. If I have an O2n vector model, I can fix maximally n charges. That's the size of the Carlson subalgebra. And the symmetry breaking happens as follows, that from O to n, by fixing these k charges, it goes down to UK. And the VEV of the ground state will break that down further to UK minus 1. If we keep asking to have a homogeneous ground state, it turns out, though, that I cannot fix these k charges individually as I want. I have to fix the sum of them. Otherwise, you will get an inhomogeneous ground state, which is harder to deal with, but Simeon actually knows how to deal with these things to some extent. So what happens here, we have, of course, more stuff going on than just in the O2 model. We have one relativistic Goldstone with a dispersion that goes like P, and K-1 non-relativistic Goldstones with a dispersion like P square, and they count double. And that is actually related to what Hitoshi was pointing out yesterday. He and Watanabe studied this type of thing, so we were able to make use of these results. We didn't have to reinvent the wheel here. And in fact, if you do the counting, one relativistic plus 2 times K-1 non-relativistic, that's exactly the dimension of UK divided by UK-1. So what you get here from the symmetry breaking. It turns out that when you go to large charge, the non-relativistic Goldstones are also pressed by inverse powers of Q. So the end result is very similar to what we had in the O2 model. The low energy physics is again governed by the one relativistic Goldstone that we had. It turns out that the formula is the same for the anomalous dimension, where the exact values of these two numbers is n-dependent. So this looks different depending on what vector model I'm looking at. But here the Casimir energy is universal for any n of the vector model. Also for this, we have some confirmation of the lattice, but this is all data that we used. So you see, in the day, they only managed to go up to charge 4, which isn't exactly a large charge. But they did it for several different vector models. And you see, even though this is maybe less convincing as it doesn't go very high up, the agreement is very good and only starts to fail somewhat for small charge, for which in any case, we weren't aiming to make a claim here. But we can go even beyond the vector models. And the next natural step would be to study models where the order parameter is now not vector valued, but matrix valued. And of course, we need the symmetry. These models have a global SUN symmetry. The easiest case to study, algebraically speaking, is the SU3 matrix model, again in 3 dimensions. And it turns out that very similarly to the vector model, I can only fix one U1 charge if I insist on having this simple case of the homogeneous ground state. But in some sense, not much new is happening. The same happens as in the vector model. We have, again, a single relativistic Goldstone boson that governs the low energy physics in the case of large charge. And the anomalous dimension has, again, the same form as for the vector model. We also calculated the 3-point functions because you can basically get all the CFT data in this sector. This was work done in collaboration with my student last year. Last year. Oh, sorry, this should have been, it was this year. Sorry, I'm confused. And going beyond this, actually more interesting things happen when you go up to SU4. New effects appear. For example, there's now enough room in the algebra, so to say, that it is possible to fix more than one U1 charge while still retaining the homogeneous ground states. So we get 2 different IR fixed points that look different at large charge. One is with 1 fixed charge, one is with 2 fixed charges. This is a project my student is working on by himself these days, and that will appear soon. Okay, I'm almost done with what I wanted to say, so let me summarize. We have seen some very concrete examples where a strongly coupled CFT simplifies in a special sector, the special sector being the one of large charge associated to the global symmetry. We were able to have a general treatment for the O2N vector model in 3D, and we've seen that in the limit of the large charge, we could compute the conformal dimensions, which has the following universal form, where just these numbers here will change for the different models. And we've also seen that we can apply this beyond just the vector model. In fact, we're looking at the smaller n matrix models at the moment. This is a very young subject in some sense, so we have only just started to exploit this method. So there's actually very, very many things one can and should do from now on. I've been focusing on the homogeneous ground state, but of course, there are the non-homogeneous ones, which is something Simeon has started working on with his student. Then, of course, these have been bosonic models. An obviously interesting question would be what happens to fermionic models at large charge, and will it all work the same? One can study supersymmetric models at large R charge, also something that Simeon's currently involved in. And the obvious question is, since we have the ADS-CFD correspondence, we have here the CFD side, the question is what happens on the gravity side in these sectors of fixed charge? People have been working on systems with large spin. Can we somehow make contact to that? So far we couldn't. And another very interesting question is to study dualities in sectors of large charge. Then the relation to the conformal bootstrap is, of course, an interesting one. Can they use our results? Can they check our results at large charge? And even though the paper is not out, they are working on that, so that's something that is currently happening. And in a more practical way of thinking that matters for the universe as we know it, can we use this approach of large charge somehow for studying actual QCD? So there are incredibly many things to do, and I hope many other people will also start looking at this. I think this is really a fruitful direction that we have started here at IPMU. And with this, I'm done with what I wanted to say. Thank you very much for your attention.